Welcome to the training session on atmospheric rivers. I'm Dan Bicus from CIRA. Ed Zoke and myself developed this training. For our learning objectives, we'll be using GOES-R imagery, RGBs, and products in identification and tracking of atmospheric rivers. In this lesson, we'll use GOES-16 products and imagery for an atmospheric river event that impacted the Mid-South Mississippi River region in April of 2025. We'll also look at various products from polar orbiting satellites to see how this data complements and supplements what is available from GOES for analysis of an atmospheric river. An atmospheric river is a relatively narrow, in width, swath of high moisture extending from the tropics or subtropics into mid-latitudes. They are important because they can lead to significant precipitation events that lead to flooding. The most well-known atmospheric river events occur in the East Pacific, extending roughly from Hawaii into the west coast. The media sometimes refers to these as the Pineapple Express. It's important to know that atmospheric river events can be found in the Gulf of Mexico and other parts of the Atlantic, and that is where our case study of interest occurs. Sometimes the atmospheric river is enhanced by moisture from a tropical system and can lead to excessive rainfall events. The effects of atmospheric rivers can extend far inland. For more information on atmospheric rivers, I'll include some links under the references here. What's new in the GOES-R era to help us diagnose atmospheric rivers? In terms of qualitative evaluation, there are 3 water vapor channels versus just 1 previously, as well as new RGBs. For quantitatively evaluating an atmospheric river, we have products from GOES that can provide the magnitude and areal extent of total precipitable water, and also rainfall rate. These products are improved over past versions of these products that existed in the pre-GOES-R era. There are training modules on the GOES TPW and rain rate products available for more information on the products. Data from polar orbiting satellites provides valuable information on atmospheric rivers, including the blended TPW and rain rate products, as well as the CIRA advected layer precipitable water, or ALPW product. The atmospheric river event that we'll focus on occurred in early April of 2025. We'll focus on a 3-day period within this event that spanned a longer time period, so keep in mind storm totals for the entire event were even higher, which led to significant flooding. The image depicts the MRMS radar-derived quantitative precipitation estimate, or QPE, for the 48-hour period up to 12Z April 6. A large area of greater than 4 inches, depicted in red, occurred in western Kentucky, southern Illinois and Indiana, southeast Missouri, Arkansas, and western Tennessee. Localized higher amounts of greater than 8 inches are depicted in white. We'll start with all 3 water vapor bands from GOES-16 along with the air mass RGB. We'll look at hourly imagery to span a long enough period of time, essentially midday April 4 to the evening of April 6. On the large scale, the water vapor imagery depicts a trough across the western and central U.S. with a ridge centered over the Caribbean. In between the trough and ridge, we have a frontal boundary that acts as a source of lift for convection centered over the Mid-South Mississippi Valley, before moving eastward near the end of the loop. Multiple rounds of convection that occurred over roughly the same area led to significant flooding. Although we're not able to detect low-level moisture in the water vapor bands due to the weighting function profile being too high in altitude, we get an idea of the flow around the ridge, which leads to southerly flow across the western Gulf of Mexico, which would advect moisture from low levels northward. We'll get a better idea of this when we look at precipitable water products later. We do get a sense of the mid to upper level flow in the water vapor imagery, since this is the altitude in the weighting function profile where the water vapor bands see the best. We can see a connection to a plume of mid to high level moisture coming from the subtropical region southwest of Mexico, northeastward towards the Gulf of Mexico and the U.S. Gulf Coast. It shows up best in the upper level water vapor band at 6.2 microns, but also in the mid-level water vapor band at 6.9 microns too. Next, we'll look at a 4-panel display during the daytime hours of April 4 of GOES IR, mid-level water vapor, and visible bands, along with the MRMS composite reflectivity. This allows us to focus on regions of developing convection in the visible and IR bands relative to the flow pattern we observe in the water vapor imagery, and we can also see where it is precipitating with the MRMS composite reflectivity. Abundant moisture is coming from the Gulf of Mexico towards the frontal boundary where convection keeps developing. To really get an idea of the moisture plumes associated with the atmospheric river, we need to look at precipitable water products, so we'll look at that next. This is the GOES total precipitable water product for the daytime hours of April 4. Since this product is based on IR channels, cloud obscuration prevents detection of precipitable water. Therefore, it is only useful in regions that are clear or mostly clear. I've overlaid the GOES visible image to indicate where clouds are that prevent observations of precipitable water. High total precipitable water values exist on the western edge of the ridge, centered over the Caribbean, and the flow pattern advects these higher moisture values northwards into the southern U.S. Gulf states up to the frontal boundary, allowing for heavy precipitation associated with convection. The GOES TPW product is at 10 kilometer horizontal resolution and is available every 5 minutes. However, I show a reduced number of images in this animation to cover a longer period of time. In this 4-panel display, we are looking at total precipitable water depicted from 2 different products on the top 2 panels, and on the bottom 2 panels we are looking at rainfall rate expressed in inches per hour from 2 different products. Starting with the upper right panel, this is the GOES total precipitable water product like we just looked at on the previous slide. The product is available every 10 minutes, but I've time matched this animation to the blended TPW product to produce a longer animation. Note that cloudy regions are masked out. In the upper left panel, we're looking at the blended total precipitable water product. This product is hourly and on a 16-kilometer grid. The blended TPW product makes use of a combination of 3 different data sources. The first is the GOES TPW, which is the same as the upper right panel, but it also includes TPW from microwave instruments on polar orbiting satellites, as well as surface-based GPS occultation data. TPW can be retrieved over cloudy scenes in microwave instruments. The exception would be precipitating clouds, which is why some regions are masked out. The blended TPW product complements the GOES TPW product in that it offers data over cloudy regions where GOES cannot make retrievals. On the other hand, the GOES TPW product has data available every 10 minutes, while the blended TPW product is available hourly. Use these products together in tandem to overcome each other's weakness and build upon their strengths. Similarly, the GOES rain rate product, shown in the lower right panel, is available every 10 minutes, but not as accurate as the blended rain rate product, which makes use of both GOES and microwave instruments on polar orbiting satellites, and is available hourly. Rain rate data from microwave instruments is of higher quality than that obtained from GOES. Use these products in tandem to overcome each other's weakness and build upon their strengths. In this particular case, the highest rainfall rates are over CONUS, but in the event of an atmospheric river over the ocean, keep in mind that rainfall rate data from radar would not be available. TPW data derived from satellite instruments is an extremely useful way of analyzing the moisture plumes associated with atmospheric rivers, and also offers a direct comparison with NWP guidance via the readily available TPW field. Rainfall rate data provides where and how much rainfall is occurring to help identify regions of excessive rainfall. One of the more recent developments is the ability to view moisture in different layers from microwave instruments on polar orbiting satellites. The advected layer precipitable water product is constructed by taking retrievals of moisture from microwave instruments on multiple polar orbiting satellites. Data swaths are advected up to 9 hours before a common time via GFS wind forecast and average. 4 layers are created, and the product is created hourly, valid at the top of the hour, and exist on a 16-kilometer grid. The product is available in cloudy regions, but not in precipitating regions. In our case, if we look at the lowest layer, which is the surface state 50 millibar layer, we see rich moisture from the Caribbean advect northwards towards the Gulf coastal states, being on the western edge of the ridge over the Caribbean. This rich low-level moisture advects towards the frontal boundary where convection develops and results in significant rainfall. The 850 to 700 millibar layer depicts a similar scenario. However, as we move up to the 700 to 500 millibar layer, we see a moisture plume with origins in the Pacific Ocean southwest of Mexico, moving northeastwards towards the frontal boundary. A similar scenario is depicted in the 500 to 300 millibar layer, but keep in mind with both of these upper layers, the moisture values are lower than the values observed at lower layers. One thing we can do to make the patterns in the upper layers more readily visible is to change our data range, which we'll consider next. Here's the same ALPW product we just looked at, except I've changed the data range on the two layers at upper levels. At times you may need to change this, particularly for the 700 to 500 and 500 to 300 millibar layer, depending on the moisture values for a given day. The way the data is displayed is with a data range of 0 to 3 inches. However, values greater than 1.25 inches are masked to a pink color. Reducing the upper limit of the range will make more features readily visible as they extend into more colors. In this example, we've modified the data range of the 700 to 500 millibar layer to be 0 to 2 inches, and the 500 to 300 millibar layer has been changed to 0 to 1 inch. Notice how much easier it is to see moisture patterns at the upper levels. These can be important to identify in terms of enhancing precipitation efficiency with deeper moisture. Keep in mind the values of moisture though. In this case, the low-level moisture from the Gulf of Mexico is the dominant moisture source, although there is at least some moisture coming from the Pacific at mid to upper levels, which may be leading to deeper moisture profiles over the frontal boundary region. Let's briefly look at an atmospheric river event in the eastern Pacific Ocean that affected southeast Alaska in April of 2025. In the upper right panel is the surface to 850 millibar layer ALPW. In the upper right panel is the GOES mid-level water vapor band at 6.9 microns. In the lower left panel is the blended rain rate, and in the lower right panel is the blended TPW. Start with the GOES water vapor band for analysis of the mid to upper level pattern, noting locations of troughs and ridges. Use precipitable water products to analyze the plume of moisture associated with the atmospheric river. In this case, the moisture plume has origins in the vicinity of Hawaii and extends northeastwards towards the southeast coast of Alaska. Finally, assess rainfall rates with a rain rate product. In this case, I chose the blended rain rate product since it's not a rapidly evolving convective event. And recall that GOES rainfall rates perform better for deep convection versus stratiform rain. This event is primarily stratiform rain, so the input of the microwave instruments in the blended rain rate product has greater value in this scenario. In summary, the GOES-R series aids in atmospheric river identification and analysis, that is qualitatively using information from some of the new bands, products, and RGBs, and quantitatively using other products, including precipitable water products and rain rate products. Data from polar orbiting satellites complements and supplements what is available from GOES. Use GOES and polar orbiting satellite data in tandem for the best possible analysis of an atmospheric river.